Good day friends, welcome to my channel lecture series on power electronics. In this lecture, we will be seeing the operation of a single phase full wave bridge rectifier, especially the controlled full wave bridge rectifier. Rectifiers convert AC to DC, that is a bidirectional input is converted into a unidirectional output when rectifiers are used. They are classified as uncontrolled rectifiers and controlled rectifiers. It is called as an uncontrolled rectifier when diodes are used. It is called as controlled rectifiers when thyristors, especially SCRs, are used. Rectifiers are classified based on the input supply as single phase or three phase, based on the quadrant of operation as one quadrant, two quadrant or four quadrant. Based on the number of pulses available at the output, it is classified as 1 pulse, 2 pulses, 6 pulses or 3 pulses. Here in this lecture, we will be knowing about the operation of a single phase, 2 quadrant, 2 pulses rectifier. Rectifiers are used mostly in DC motor speed control. If a variable input DC is required for a DC motor, it can be obtained from a rectifier. DC supply for inverters. Inverters convert DC to AC. The input to an inverter can be from a rectifier. Then in electrochemical processes also it is used. DC traction. Traction means in the railways. HVDC transmission, high voltage DC transmission. In all these applications, rectifiers are used. This is a basic circuit of a single phase full wave controlled rectifier. The name is controlled rectifier because we are making use of thyristors here, SCRs here. There are 4 thyristors. The numbering is given as T1, T2, T3 and T4. The input is AC, output is connected to a load. This load can be a resistive load or RL load, or it can be even a motor. So in this circuit, we have shown a resistive load. Let us see the operation of it. Thyristor will be forward biased when a positive is available to the anode, negative is available to the cathode. So during positive half cycle, at this junction, the voltage is going to be positive. Here it is going to be negative. So this positive here will make the T1 forward biased. The anode is getting plus over here. The cathode is getting plus. So T4 is reverse biased. T1 is forward biased. Here when it is minus, the T2 thyristor is getting forward bias because negative is available to the cathode, and here if we see T3 is reverse bias because negative is available to the anode. So during positive half cycle, this junction is positive and this junction is negative. During negative half cycle, this junction is negative and this junction is positive. We see in this picture, during positive half cycle, T1 and T2 will conduct if the gate pulse is given. They are already forward biased. So when the gate pulse is given, the current flow will be from the supply through T1, through the resistive load, through T2, back to the supply. During negative half cycle, this junction becomes negative, this junction becomes positive, as already mentioned. Because T3 and T4 are forward biased, if at this time the gate pulse is given for T3 and T4, the current flow will be from the supply through the point plus, through T3, through the resistive load, through T4, back to the supply. The current always flows from plus to minus. So if we compare these two diagrams, in the first case, during positive half cycle, the current flow in the load is from top to bottom in the resistive load, that is in this direction. If you see in the negative half cycle also, the current flow is from top to bottom. So from a bidirectional input, we are able to get a unidirectional output. So by properly giving the gate pulse to T1, T2, then switching them off giving to T3, T4. From a bidirectional input, we'll be able to get a unidirectional output. We see the voltage and the current waveforms. During the positive half cycle, T1, T2 conduct. During negative half cycle, T3, T4 conduct. Of course, during negative half cycle, we get the current in the same direction in the load. And if you see the current waveform, it looks similar to the voltage waveform, except that the amplitude is reduced. If the firing pulse is given at the 0th instant, we get a full pulse. And if the firing angle is given at a later stage, we'll get only the part of the pulse as shown in this diagram. So if the firing angle alpha at some value of alpha only, the current is flowing through T1 and T2. So the voltage waveform is starting from here only. Here we are getting an amplitude which is different from that of the full firing angle. The values of the average output voltage can be obtained using the formula VDC is equal to 2Vm by pi into cos alpha, where alpha is the firing angle. IDC can be obtained by dividing the VDC by the resistance value. RMS value of the output voltage can be obtained using this formula. Vm is the maximum value of the voltage. Vm by R into 1 by pi is pi minus alpha plus half of sine 2 alpha root of it. RMS load current can be obtained by Vrms by R. So in this lecture we have learned the operation of a single phase fully controlled rectifier. Thank you. Let us simulate a full wave rectifier uncontrolled. By uncontrolled, what we mean is we are going to make use of diodes and the output is going to be a constant DC voltage. A full wave rectifier converts both the positive as well as the negative half cycle of the input voltage. For that, let us first open a new project, and for this we need 4 diodes. So let us take 4 diodes and place them in the window. We need a voltage source, a sinusoidal voltage source. We can take a sinusoidal voltage source from the library. We need a load, which is a resistor. We'll take that also and place it here. We need measurement probes. We'll take 2 voltage probes from the library. Place one on the input side and one on the output side. Now let us connect all the elements by using the wire. Let us connect the diodes like this. Let us connect all the diodes. The excess lines which appear can be just selected and deleted. Now this voltage source is connected to the junction here between 2 diodes. Positive is connected in one of the junctions and the negative is connected to the next junction. So the junction between the other 2 diodes is connected from the source. Now the resistor is connected to the junctions of the diodes using the wire like this, and we have the voltage probe connected to the input side. So let us be first clear of what we have here. The voltage probe has got a plus this side, and so it has to be connected to the positive. Let us rotate it and then connect it, or let us even take another voltage probe and place it properly. the plus terminal should be pointing towards the top. That is, it should be connected to the positive of the voltage source. So if it is not connected this way, the output will be shown as a cosine wave instead of a sine wave. So now let us connect the voltage probe to the input side and to the output side also. Now the circuit is ready. We will give all the attributes. Let us choose this voltage source and give the attribute. Let us take the voltage as 220 volts and let it be the circuit frequency is 50 Hertz. Let us display it as V in and let the voltage and the frequency be displayed. We are checking the boxes. Now let us give the attributes to each of the diodes. Let us name this diode as D1 and we are not going to change any component, any other components, any other attributes there. We are going to name the second diode as D2. By checking the box, we see that it is visible. Here also D1 should be made visible. So we'll check the square box here. We'll name this diode as D3 and we'll check the box. This we will name it as D4. Normally the numbering is so given that it will be easy for us to understand the operation of the rectifier. So during the positive half cycle, the diode D1 and D2 will be forward biased. So the current flow will be from the positive of the supply through D1 through the load to D2 back to the supply. During negative half cycle, the diodes D3 and D4 will conduct because during negative half cycle, this point will become negative and this will become positive. So when this point becomes positive, the current will flow from the supply D3 load back to D4. So now we have to keep a simulation control also here. Let us make the timing as say 0.05. Now when we run the simulation, we can even give the probes the attributes as V in and V output. We can check the boxes so that it is displayed, and for this we can give the attribute as V out, and this is also displayed. Let us now simulate. When we run the simulation, we will see the V input. As before, we'll change the thickness of the wire as 3 and observe that the voltage, input voltage is a sinusoidal waveform. Let us now add a screen and here we choose V out. The color we are by default taking as blue color and then the thickness of the wire as 3. We see that we get an output which is a cycle which has only positive cycles. During the negative half cycle of the input supply also we see a positive output voltage. So this is how bidirectional input voltage is converted into a unidirectional output voltage which can be which has ripples, and these ripples can be filtered using a suitable capacitor in the circuit. So this is how we simulate a full wave rectifier uncontrolled. Here we have made use of the diode. Let us now simulate a full wave rectifier controlled. By controlled, what we mean is we are going to make use of thyristors instead of diodes. So similar to a controlled rectifier half wave which we have already seen, here also we are going to make use of thyristors. So we will open a new file and we will make use of the thyristors. We will find the thyristor here in the power elements. So we will take one of the thyristors, drag it and place it here. For a full wave rectifier control, we need 4 thyristors. So we will keep 4 thyristors, 1, 2, 3 and 4. And we need a voltage source similar to that of a full wave uncontrolled rectifier. We will take a voltage source, place it here. We need a load resistor, we will take and place it here. Then we need to have the probes for measurement. We'll take the voltage probes, place it here, one on the input side and one on the output side. So excess one can be deleted. Now, because it is thyristors, we need a gating block for every thyristor. So we'll take the gating block here, we'll take it and place it here. For every thyristor, we need a gating block. So we need a gating block for 2 thyristors at 1 degree and another 2 thyristors at another degree. So let us first connect the thyristors like this using the wire. As we have done for the full wave uncontrolled rectifier, and we will connect the voltage source also as we have connected in the uncontrolled rectifier. Then we will, because there should not be any connection of the gate with that of the source, so we will connect it again. We'll take it like this. You can stop it wherever you want and then we can take it and connect it here. Now we need to connect the resistor to the thyristors. We are connecting it like this. The resistor end is connected. Let us assign the attributes now and we will connect even the voltage probes. Say on the input side like this, on the output side like this. We will give the attributes, and here we have to see that we are going to give the gating block. The gating block is connected for the thyristors. That we will first attribute the thyristors as we have put it as T1. Display it. We'll mark this as T2. Display it. Then we'll mark this as T3. Display it. Mark this as T4. Display it. Now we have to give the gating block connection for thyristor T1 and T2 from the same block, and for T3 and T4 from the same block. We can have this one placed elsewhere, and here we can give an attribute like 0 and 180 degrees. We'll put 0 and 180 degrees means the full wave positive half cycle will be rectified. So these thyristors T1 and T2 conduct from 0 to 180 degrees, whereas the thyristors T3 and T4 conduct from 180 to 360 degrees. So let us have this 0 to 180 degrees for the thyristors T1 and T2. Let us take a wire and connect it to the gating block, and this gating block should also be having a gating pulse. This we can connect. Stop it there, take and connect like this. And this while doing this, this T3 is also getting connected, so that is wrong, it has to be deleted. While connecting, it should be done properly. Now let us take this wire and connect T2 properly. That is, we'll take it for little more longer distance so that T3 is not getting connected over there. Now we have brought it to T2. So we see that T1 and T2 have the same gating block connected. For T3 and T4 we have to have this gating block, and the attribute for that is going to be 180 and 360 because they conduct from 180 to 360 degrees. And here the frequency also should be marked as 50 hertz. Here also in this block also it should be 50 hertz. It should not be 5000. So now we have made all the connections. We'll make a simulation control also here, and we'll see that the time is made as 0.04 or 6. We'll see for 2 cycles, so 0.4 we will make it. And now we have this voltage also, voltage to be given as say 220, 50 hertz. Mark it as V simply, and we'll give the attribute for this also. Input voltage flow V in, will display it. We can have this output flow V out. Now we can have everything is done. Now we need to have the connection for T3 and T4. We are ready to do it. So though we have made it as 180 and 360, we have not connected. Now let us connect it to the gate. T4 is connected. Now we can connect the same line. We can connect T3 also. Done. So this is the entire circuitry, and now we can simulate it. We see that the input and the output voltages look like this. The positive half cycle as well as the negative half cycle is shown here in the input side. In the output, we see that we have only the positive halves. Here we have seen that the firing angle is 0 for two thyristors and 180 degrees for the other two thyristors. Let us now change the attributes and see. Let me make the attribute of this gating block as 30. We can make it as 30 and 180. So here for the second gating block, it is 180 plus 30, which means it is 210. So 210 and 360. Now let us simulate again. We'll run the simulation. We will see the input and the output like this. As this is the input voltage, we'll add a screen. We'll see the output voltage in blue color. We'll choose the thickness as 3, and we will see that the output is available from 30 degrees to the 180 degrees, then from 210 degrees to 180 degrees. So here we see that the output voltage is slightly lesser than the output voltage which is available when the thyristors were triggered at 0 degrees. Let us now simulate for another value also and check. Now let us give the attributes as 90 and 180 degrees for the thyristors T1 and T2, and for T3 and T4 let us give the that is the 180 plus 90 will be 270. So it will be 270, 360. So let us simulate and see the output. We see the output. This is the input voltage, which is a sine wave, and we want to see the output voltage. We'll see it in blue color. We see it as 90 degrees. When 90 degrees is given as a firing angle, we see output like this. So a full wave rectifier, a controlled rectifier, can give different values of the output voltage, which is unidirectional, and based on the firing angle given for the thyristor, the output can be changed.